All right, let's go ahead and get started. In your notes, you'll have to worry, and I have them. I have to put them in the grade book. So in your notes, if you have your notes, if you don't, then just get a separate sheet of paper. You need to write these things down. Write them down. Okay? What are valence electrons? What are they? Yeah. Very good. The outermost shell or the outside of an atom. That's perfect. You are going to do very well on that question tomorrow, Jaden. Okay? The quiz tomorrow. I don't. How many times did I just say we had a quiz tomorrow?
No, I know that. Like 7 times. I thought it was just going to be the.
It's the whole. It's everything we've talked about. No. Yes. Mm-hmm. What are valence electrons? I'm working through this bullet point by bullet point. They are the electrons in the outermost shell. That is in your notes. Or if they're Emma's notes, they're in my. Yeah, I know. It's going to be a tricky. Okay, so what we need to do is I'm going to show you today how to use the periodic table to find valence electrons. Okay? Valence electrons are their outermost electrons, and there's a trick to the periodic table to figure this out without needing your sheet. Okay? All right, so if you take a look up at the periodic table, take a look at the numbers at the top of each column. Here above lithium is a number 1. Here above beryllium is a number 2. If boron, carbon, nitrogen, oxygen, fluorine, and neon, it's 13, 14, 15, 16, 17, 18. So here's how this works. Column 1 has 1 valence electron. It's no coincidence that the first column has 1. The second column, hey, look at the top, there's a 2, has 2 valence electrons. There's no coincidence that the second column has 2 valence electrons. There's also no coincidence that the 13th column has 3, the 14th column has 4, the 15th column has 5, the 16th column has 6 valence electrons, the 17th column has 7 valence electrons, the 18th column has 8 valence electrons. That is not a coincidence. Columns 1, 2, 13, 14, 15, 16, 17, 18 are called representative, meaning that the column number indicates the number of valence electrons that they have. Isabella.
So, does that mean column 3 only has 6 and so on?
We don't touch these because, no, they don't correspond to the pattern. That's what these transitions are weird. So just columns 1, 2, 13, 14, 15, 16, 17, and 18. GP.
Are you going to leave up the periodic table?
I will. I'll probably even give you your own personal copy of a periodic table for the quiz. Yes? Okay. So, if I find phosphorus, look over here, P, and I go up, it's column 15. So how many valence electrons does that indicate? 5. Yep. And if I find chlorine over here in the halogens, I go up, it's 7. If I find boron, it's in column 13, and so it has 3. And if I go to magnesium, it's in column 2, so it has 2. If I go to lithium, it's in column 1, it has 1. And oxygen is in column 16, it has 6. So you don't need that sheet I gave you because it's right there on the periodic table by the way that it's labeled. Okay? I will give you a packet of resources that you will be allowed to use tomorrow, but please understand that I would hope that you would try to pick up on this method. It will be very useful to you later. Okay? Just so you know, when I normally do this unit on chemical bonding, it's 2 units when I taught it in high school. And it was the equivalent of about 250 slides of information on a PowerPoint. Not to mention, it took me about a month and a half to deliver the material. So I'm giving you the incredible short version of it, okay? This is like the super short version of what I normally take much longer to teach. I was looking through the presentation this morning. Just covalent bonding presentation was 137 slides. Okay?
How'd you do that all in one day?
I didn't. It took me weeks.
We don't even have you for weeks.
I know. That's why I have to do the short condensed version. Okay? All right. Oh, a lot of it. Yeah. This is why it's so good that you get some of these basics down. You'll have to go back online. Why do atoms bond? Okay? You'd be better off writing down key ideas, okay, and printing these off. But you have to print them off. If you think you're going to, hey, I'll go home and print them off, and then you don't, well, then that's just a waste of time. All right, so atoms form bonds to become stable. They're unstable. They want to bond. They're looking around for a mate. It's kind of like humans. Humans are like, oh, eventually they're like, I want to marry. Most of us, okay? There are some that don't. There's some, but for the most part, everyone's like, I want to mate. I want a partner. I want to bond. Atoms form bonds to become stable. I was much more unstable until I met Mrs. Bornheimer. Then we got married, and I calmed way down.
Did she make you become sane?
Stable.
So you're still insane?
Stable. Okay. Stability is directly related to the energy that an atom possesses. Okay? So typically speaking, we would say that an unstable atom has a lot more energy, and a stable atom has less energy. That's not always true, but that's pretty accurate. So what we're really looking to do is when atoms come together and form bonds, oftentimes, not always, but oftentimes, energy is released. Okay? It's kind of like like when we see fire, that's a chemical reaction that produces heat and light, and we call that fire. Okay? So atoms are really forming bonds because naturally that's the state they want to be in. Okay, atoms float around looking for other atoms to bond with. Now, those bonds aren't always the same and they take different forms, but for the most part, they're looking to form bonds. That's what they want. Okay, that's what they desire above all else. Okay, so first bullet point, atoms form bonds to become stable. Second bullet point, stability is directly related to the energy that an atom possesses. Okay, third bullet point, there are 4 blanks. You might want to jot them in the margins as I say them. Okay, in order to become stable, and then there really should be a comma there. So stable, comma, I think. My grammar is, okay, good. In order to become stable, comma, my English teachers are smiling right now. Atoms need to achieve a full outer, O-U-T-E-R, energy shell. So in order to become stable, comma, atoms need to achieve a full outer energy shell of 8. Ooh, there's that number that we've seen before. Valence electrons. So the whole idea behind bonding is that these atoms are trying to achieve or be connected to 8 valence electrons. For some reason, God has designed it so that these 8 valence electrons give the atom stability and the ability to bond. Savannah. It's called the octet rule. Do you know what the word octet means? 8. Yep. You think about an octagon or an octopus. Okay. So anytime you see OCT, that usually indicates 8. Okay. So 8's kind of like a special number for atoms. Yeah. So this is literally, not to be like really over the top, 8 valence electrons is the goal. So the octet rule, basically the rule of 8. The rule of 8, not 7, not 9, but 8.
What about 7.9?
No partials. All right. So, a chemical bond is a force that holds 2 or more atoms together. It's a force, not to be confused with the Force or Luke, I am your father, or Star Wars, okay? It is literally just a force, a natural force that exists to bring 2 atoms closer together. This all happens with the electrons. Because this has to happen on the outside of an atom. Okay? It's kind of like when I do a handshake, I don't do a handshake with my lung. Okay? Weird. All right? I take and I extend my exterior appendage, my hand, and I shake someone's hand. Okay? I'm using the outermost part of my being. Okay, that's what atoms do too. When they combine and they meet, they're using the outside of themselves. So there are really two main types of bonds, and we've been talking about them, so this is no coincidence that we have ionic bonds and covalent bonds. Yes. Ionic bonds and covalent bonds. Okay, so chemical bonds are when they come together. It's like a meeting. It's like a happy reunion. Oh, hey, boy. Okay. We're going to get to metallic at the end. Okay. Metallics are unique. There are metallic bonds, but because it doesn't really fall into this, well, it does. You're right. If you want to add it here, you can, but it's got its own section. I don't want us to get confused. Caleb.
So isn't Ionic the one steals from the other?
Yes, there's a stealing that's taking place. Very violent, yes.
They
Covalent, they share.
metallic a bunch of them.
Yes. Oh, very good. Oh, that's very good. You're going to do well tomorrow. All right. Quickly, with the people at your table, figure out, I'm trying to just kind of remind you of some things. Locate the following families. No, you don't need to write this one down. Just look at the periodic table and just talk to the people next to you. Give them numbers. Okay, so for instance, the halogens are 17. Okay, column 17. Okay, 17. They have, oh, yes, they do. They have 7 valence electrons, Parker. Okay? You're just identifying which column number they are. So noble gases, which column number are they? They would be 18. 18. The rare earths are weird. They don't have a column number. Yes, oh, very good. And transitions, too. They don't have a column number. Mm-hmm. That'd be a very good way of describing it. Okay, I think we've got it. I've heard some good things. The halogens are 17. The noble gases are column 18. The rare earths are the two big rows at the bottom, mostly radioactive elements. The alkalis are the first column, and the alkaline earth are the second. A good way to remember that, alkali is shorter than alkaline. Shorter people come before taller people. Okay? You're number 1, my friend. Then transition metals, okay, are that big block in the very center of the periodic table, 3 through 12. All right. For the next 3 or 4 slides, maybe more, we're going to talk about just ionic substances. Okay, just ionic ones. There is some really cool features about ionic compounds that I want to bring to your attention. And I don't necessarily want this up on the board. What I want you to realize is that ionic substances are what 2 types of elements? Metals and nonmetals. Okay? Covalent substances are what? Nonmetals and nonmetals. And metals are just metals. Okay? So if I have metallic bonds of copper, well, that's just metals. There's no nonmetals in there. Okay? So you have literally all 3 scenarios. You have just metals, metals and nonmetals, just nonmetals. If you think about it like that, it's pretty easy to narrow down. I'll even write it on the board. So metals and nonmetals, and then just. You have all 3 scenarios. So you have one by itself, a combination, the other one by itself. These would be metallic bonds. Actually. These are ionic. These are covalent. Okay. If you want to put it in your notes, you could put them like metals only form metallic bonds. Metals, when combined with nonmetals, are ionic. Nonmetals all by themselves are covalent.
Oh, so you just line them up.
Yeah. Yep. So I'll even put little dots. You could if you wanted to. That's sure. If you don't have to put a dotted line. All right. Has anyone ever seen a crystal? A real crystal, like that formed in nature? Okay? Like a diamond, sure. You've probably seen a diamond if your mom has a diamond ring, or your dad. Uh, how many of you have ever seen a geode that has crystals formed inside it? It's a rock that you break apart and it's got crystals inside. Okay? Those are really neat too. Ladies and gentlemen, those kinds of substances, geodes, crystals, not diamonds, but crystals that form in the earth are typically ionic because of this idea here called a lattice structure. What does this look like to you here on the right-hand side?
Square.
Yeah, but what?
Cube.
Okay, a cube, a solid, a square, okay, in three-dimensional cube. Have you ever played on a jungle gym? Okay, it's like a jungle gym. It's got interconnected pieces that are combined by bonds. Okay, this is what we call a lattice structure. I'm gonna come back to that other slide. You don't need to write this one down, but basically what it means is it's a three-dimensional geometric arrangement. Okay, it's these different atoms that have been kind of placed together.
We don't need to write that down?
No. Ionic bonds form this naturally, which is so neat. If you find an ionically bonded substance in nature, it will always have a three-dimensional shape to it. Real weird. Most minerals found in the earth are ionic, and most minerals, okay, have some kind of geometric shape. It's crazy. It's really cool. Okay, really cool. All right, I even have a short video for us today showing you the formation of these crystals in a that I made a couple weeks ago that was time lapsed. It's really neat. Yeah.
When you say like crystals, do you mean kind of like our birthstones?
Kind of. Yeah.
I have a whole bunch of my birthstones. Mine's green.
All right. The next thing you should understand is that when ionic substances are in water, they form what is called an electrolyte solution. There's electrolytes in some types of water. There's electrolytes in Gatorade. There's electrolytes in Powerade. Okay.
Any like sports?
Yes. Electrolytes are basically a substance or a liquid that has an ionic substance in it. It's dissolved, like you dissolve salt in water, salt water. Salt water is electrolyte. It allows electricity to be conducted. Okay.
Electricity and like that Gatorade. Do we need to know all of these?
You will need to know some of these. Yes. Yes. So I would actually write them down. Take note of everything I'm saying. Yes.
I wrote this down and wrote them all.
Yeah.
Like put them all together. Try to just go on to the next page and tell them what they mean.
If you don't have room, then yeah. Okay. Savannah.
So would there be like electrolytes and
There is an electrolyte probably in just about every solution you drink. The reason is we drink to fill our body up with electrolytes. That's the reason we drink water. Food's got it in it too. If you have salt in your food, you have an electrolyte in there. How many of you have ever tasted your sweat? You have no. If you're running and you get sweaty, you've tasted it. Okay, so just don't try to pretend like, oh, I've never done that. Okay, it's salty. Your body sweats out electrolytes. But here's the problem. Your brain, if you've ever looked at a human body scan of our brains and our nervous system, you'll notice it's all electrical current. Okay? That's why our bodies can actually run pacemakers. Pacemakers, okay, require an electrical current. That's why with a person with a pacemaker, if they're shocked by electricity, have to go to the hospital and have it reset. Because our bodies conduct electricity. That's how our brain speaks with our organs, it speaks with our muscles.
Wait, so how come like when somebody like or not when, like if somebody like I don't know, like if you cut yourself, how come you don't get electrocuted? Is it that?
No, it's not that kind of electricity. It's sending a small electrical signal to all the parts of our body. However, if you do get electrocuted, the electricity causes all of your muscles in your body to clench up because your body responds to electricity. Because every connection in your body is made possible by electrolytes. Yeah.
So if someone with a pacemaker, like you know when sometimes you'll touch the light switch and it'll like
Shock you.
yeah,
It's not enough.
Oh.
It's not enough. It has to be significant. Like an electric fence would be something that they would be very bad for them. Yes. Mm-hmm. Yes, Izzy.
So electrolytes cause or
Allow.
we drink electric lights because
Yes. That's exactly it. If you don't have enough electrolytes, your body slows down. You become tired. Your reflexes aren't as fast. Okay.
Oh, so that's why like it's for sports.
Yeah, that's why oftentimes it's for sports. If you sweat a lot, huh?
I drink too much Gatorade.
Some people actually have little electrolyte packets they add to bottles of water to help the water improve their.
What's in like Red Bull and stuff?
Red Bull is not. No, Red Bull is basically pure sugar, and it's just a.
Red Bull's good.
But then you crash afterwards.
Right, because you're shocking your body.
When you drink like Monsters and like energy. That's why it's not good for you.
I've never had one in my whole life.
Can we give one to Michelle and see what happens?
No. All right, ladies and gentlemen, Parker, I see you, but hang on. Bring it back in 5, 4. Thank you. That's all I'm going to go. Melting points and boiling points. Okay. For these, that's pretty straightforward. A melting point, the point at which it melts. Boiling point, point at which it boils. Okay. Are very, very high for ionic substances. As a matter of fact, ionic substances have the highest melting and boiling points. They even they need more energy than metals. I could melt steel before I could melt table salt. Okay? They have very high melting and boiling points, which means they have to get to a temperature. They have to absorb enough energy to melt for those atoms to shift apart. And I'll tell you right here now, these bonds are so strong, it takes an incredible amount of energy to break them, or to split them, or to allow them the ability to change solids into liquids, and liquids into gases. So these are very high, because the bond is so strong.
But what about when you like boil water and you put salt?
You're not melting the salt.
You're boiling it.
You're not. The water's boiling, the salt's just floating in there.
Oh, I thought it dissolved.
That's what we call dissolving. It's just floating in the water. How high does it have to get up to? For some ionic substances,
Like what's one of the lower ones?
4, 5, 6,000 degrees.
What's the highest one?
What's the highest?
Not the temperatures. The highest, ionic.
No, I mean like what's the highest temperature that
I don't know them all because there's hundreds and hundreds of ionic substances. Let me look it up. Hang on.
It's like 4
Siri. Siri, it's been a long time.
Hi, Terry.
Will you say hi before you do it? Say hi. Okay. Because I'm watching this video. Yeah.
Hi, Siri.
Hello.
All right. I've now introduced. Okay. Siri, what is the boiling point of table salt?
Checking.
You go, girl.
The answer is about 1,413 degrees Celsius.
Siri, what is 1,413 degrees Celsius in Fahrenheit?
Checking on that. 1,413 degrees Celsius converts to about 2,575 degrees Fahrenheit.
Okay. For just table salt. So let's pick something else that might even be. All right, let's do lithium chloride. Siri, what is the boiling point of lithium chloride?
Checking on that. The answer is about 1,382 degrees Celsius.
Siri, what is 1,382 degrees Celsius in Fahrenheit?
Checking on that. 1,382 degrees Celsius converts to about 2,520 degrees Fahrenheit.
You should do the melting point of like cesium iodine.
So, all right, so it's between 2,000 and 3,000 degrees. Just so we can, so that's out on the table. Yeah.
So like for a little bit of table salt, it takes that much.
Yes. 1 grain of table salt would take that much.
Wait, how much like for like this? You have to do higher.
It doesn't. No, it's the same temperature for all table salt.
Take more, right?
It'll just take longer because it all has to absorb energy. Yep, and it'll absorb it evenly. Okay, I gotta keep moving on. The hardness of ionic substances, they're very hard, but they're brittle. Okay, so that's why table salt, like if you try squeezing it in your hand, you can't really break it. Not really. but if you like smash it on the table, it shatters into pieces. Okay.
Just like glass.
Yeah, you could kind of say it's like glass. Glass is hard. If you press it, it's already laying on the table, and you push on it, it's hard. You're not going to crack it. But if you tap it on the table, it's brittle and it'll shatter.
I don't get.
So, for instance, if I push down on the screen of my iPad, it's fine. But if I take a sledgehammer to it, it'll snap.
I want to suggest showing us that.
No, I don't think so. Probably not.
That'd be fun. Try to break
Okay, here's table salt. To give you kind of an ideal representation, don't worry about the text. What I want you to focus on is that, look at how the atoms are different. Chlorine is much larger than sodium, okay? But it forms this interconnected web. This is a pretty accurate representation of sodium chloride, okay? This is what it would look like at the, what we call microscopic level. Okay? The term microscopic, you don't need to write this down, but it comes from the Greek micros, which means small. Okay, so when we talk about something that is microscopic, it means we cannot see it with our eyes. Okay? So, for instance, microscopic person. Okay? Now, if we can see it with our own eyes, it is macroscopic. Okay? Macroscopic. Like I said, you don't need to write this down. So microscopic, we can't see it with our eyes. Macroscopic, we can see it with our eyes. That without the aid of any device.
So we would just go like this. I can see it.
Well, all right, so in all reality, to be serious, you're macroscopic. We like to say you're microscopic because it's funny. Okay? Okay. This you need to write down. Ionic compounds. Substances that form ionically. They start microscopically with like an atom bonding to another atom, and then another atom comes over and joins the party, and another atom. And so what happens is it builds this cube, or it builds this geometric prism, or it builds this lattice structure, okay? It builds. It just kind of, they just keep adding on, all right? And this happens with millions and billions of atoms. Okay, it happens until the point where we can actually see it. Okay, so at some point, it goes from being microscopic, we can't see it, to macroscopic. Oh, there it is. I can see it with my eyes. Okay, and so that's kind of what it starts out as. So a great example of this is rock salt, the salt that we put on our driveways. Okay, if I take a piece of rock salt, which looks like this, going back, looks like this, going back, looks like this, going back. Okay, if I take rock salt, it's got a cube, it's got a cube, and I were to take a sledgehammer and smash it, and then take a magnifying glass and look at it. You took a cube of rock salt, and it would have broken down into cubes. Then if I take one of the tiny little cubes that broke off it and I smash it again, it'd break into smaller cubes. It never gets to a point where it does not have the shape of a cube. Ever. No. You can go home and try it, but you might need a microscope eventually. You can break and break and break and break and break table salt. It never turns into anything but a cube. It's always a cube. It's just a small cube or a large cube. The little flakes that would fall off it, if you look at it with a microscope, would be a cube.
Can't you cut the cube like down there so it can be a triangle? Why?
Because the atoms don't allow you to break like that.
You could shave it into
It would snap into cubes before you could cut it like that.
You can't do it.
Huh?
I want to make it so it's
You record your process
okay.
on film, and if I'm proved wrong, I'll give you a pat on the back.
Okay.
What if you?
Okay, so it starts at a level we cannot see, the atomic level, and works up to something we can, and then we mine it out of the earth. Believe it or not, underneath Lake Erie, okay, near Cleveland and Detroit, and underneath Detroit, are big salt mines. They've been mining salt out of them now for generations.
So my salt
Okay.
from there?
Actually, most of our salt in this area does come from there. All of the salt that we put on our roads comes from underneath Lake Erie.
My dad always plays Texas.
Salt in Texas. They ship a lot of our salt comes from there. Now, there are other salt mines, but in this part of the country, we get most of our salt from underneath Lake Erie. Yeah.
Wait, so do all ionic substances always stay in like cubes?
Yeah. Now, they're not always cubes. Sometimes they take the shape of like triangular prisms, or sometimes octagonal prisms, or different types of prisms. But they always have that shape, yes. Yeah.
Oh, okay, so yeah, they always stay in the same shape that they were.
Yeah, that they form. Yes, indeed. All right, take a look at this for a moment. This is halite, table salt. The mineral name for it is halite, Halite. This is literally how it looks when it comes out of the ground. And if I were to break it up, it would break into smaller cubes. And so what we do, rock candy is very similar, but rock candy forms a little differently. But yeah, this is rock salt. Okay? Table salt is just a ground up version of this. It's been cleaned, dirt's been taken out. Okay? And basically what we do is we just grind it up and put it in a salt shaker and sell it for money. Okay? All right, no, you don't. No. Ground up salt that comes out of the earth, yes. Yeah, that's the way that they extract it from. See, sugar comes typically from two places. It comes from sugar cane or it comes from sugar beets. Okay? And typically it's because of the way it was extracted that it's more expensive. Cane sugar is more expensive than beet sugar, but most of our sugar from this area comes from beets. Yeah. Yes.
Okay. So I watched a little video of how they mine salt, but like in the air when they mine.
Write this down.
Doesn't it like get air salty?
It does.
But they said like it can get too salty, so I put mask.
Yeah.
Like when they like mine it.
That's salt dust, and it floats in the air like regular dust does.
So is it so salt? If you have too much of it, so those people like they put masks on.
Yeah, because salt holds water, and so if you have too much salt, it actually can dry you out. Actually, that's why they used to have salted pork. If you've ever heard that done, salted pork was a way to preserve pork for years. They would take and they would put meat in salt, and it would pull out all the water, and it would preserve it. It wouldn't go bad. Somewhat, yeah. It also has to do with like it's preservation. It was like a form of preservative. Okay, we got to move on because we only have a few minutes and we haven't even got to covalent bonds yet. Covalent bonds, all about sharing. You know that. We call substances that are bonded covalently molecules. Okay, so when someone says molecule, typically they're referring to a substance that has a covalent bond. So carbon dioxide molecules, water molecules, oxygen molecules, hydrogen molecules, sugar molecules, okay? We don't call table salt a molecule. Table salt's what we usually call a compound. There is a slight and subtle difference, which really only is the type of bond. Okay, so covalent bonds usually indicate molecules. So if I say water is a molecule, that means it's covalently bonded. Okay? Is formed when two or more atoms bond covalently. Yes?
Okay, why do we have to put salt in our water? My dad will buy
When you make pasta?
No, like salt for like your shower. Like my dad buys like when you put bags of salt. He says we need more salt for like our water.
Water softener. Because it helps to pull or bond or retain the. Basically, what it does is it allows the iron not to coat your toilet and things. It's like regular salt.
So you could just
You don't want no. It's the pellets are designed to last a long time. If you dumped table salt in there, it would get used up in one sitting. It's the size of the pellet makes a difference. For that particular mechanism uses the size of the salt so that it doesn't go through it in one cycle, but it can go through several cycles.
Is that salt? So it's the same table salt?
It might not actually be table salt, but it is a salt. It might be a potassium chloride. It might be. Yeah, they have to mine it. You can make salt too by combining certain elements. It's just usually found in earth, so it's actually cheaper to mine it than it is to make it. All right. The only thing you need to understand, you can go online, ladies and gentlemen. If you need to, you can at the end of the day. Covalent substances are almost completely opposite ionic substances. Instead of having high melting and boiling points, they have low melting and boiling points. Instead of being really hard, they're not so hard. And they don't have a lattice structure. So if you know ionic, you know covalent because it's everything opposite. So covalent substances, like I said, are basically the opposite of ionic substances. So if you took really good notes on ionic, just reverse it all.
So I can put by definition. So I can put like
ionic. The opposite of ionic, the properties of covalent molecules are basically the opposite of ionic. So they're weak. They're very weak. They're very weak. They do not conduct electricity. Okay? Very good. Yeah, so like for instance, we will put oxygen or other ion or covalently bonded substances in between two panes of glass to create an insulated window. However, we would not want to put, say, any sort of ionic substance in there because it would allow heat to be conducted very easily. Yeah.
Okay, so could a substance that has 8 valence electrons bond with another substance that has 8 valence electrons? Like, will they still have 8? Like, because if you have more than 8, like, it would equal, could it still fill up 8?
If we're talking ionic, no. If we're talking covalent, it's tricky. And in which case, then, it's too complicated to discuss at this time. Okay? So, for instance, you may have already figured out that if you have oxygen and water and hydrogen and stuff combining, or I should use a better example, oxygen and carbon forming carbon dioxide. There's way more than 8 valence electrons there. But it's tricky because they're shared, not taken. And that's where the whole difference falls. They only share some, not all. And when they do share, they're sharing a total of 8. It's different.
Could they be sharing 16?
Well, I don't want to go there, Parker. I really don't. Okay? We're almost there, ladies and gentlemen. Last but not least, and this is the last slide I'm going to have you work on today. There is one very special type of covalent bond that deals with just carbon. Okay? And it's where quartz and diamond are made. Quartz and diamond. Okay. Believe it or not, diamonds are brittle, ladies and gentlemen. They are not the strongest substance out there, per se. They're hard. They can't be scratched, but they are brittle. If you take a diamond and you smash it, it can shatter into pieces. This is a different type of covalent substance. Whereas covalent substances like water and carbon dioxide are completely the opposite of ionic. There's only one type of covalent substance that is very strong, like an ionic substance, and that is diamond. That's it. Just know diamond. Diamond is the difference. Okay? Diamond. Diamonds are, but see, these are the properties of diamonds. They're very unique. They're very brittle. So Mrs. Bornheimer, twice a year, has to have her diamond rings checked by a specialist. Because if one's chipped, she can have it replaced for free. If she misses an appointment, then they no longer will give her a diamond free if it gets damaged. So ladies, if you ever have a diamond ring someday, you need to have them inspected on usually twice a year to make sure that they're not damaged. Okay? Okay, diamonds do not conduct electricity or heat. That's very good. They're very hard. That's why they cannot scratch, and that's why they always stay shiny. And basically the reason that they are like that is because like ionic substances, they're not, but like them, they form like a pyramid-type interconnected web of atoms. Diamonds are just carbon.
Is that why when you see diamonds are like circular and then they're circular, like the shape of a diamond, you said it's like a...
Yeah, yep, that's why. We cut them like that. Natural diamonds, though, also form like that. They have unique structures. They're not as pretty, but they do form something very similar.